Hello students, welcome to EPG Part-1. I am Dr. Savita Sharma from University of Delhi. Today we are going to talk on the module Solar Cells Part 1 under the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. First of all, we'll learn about why solar energy conservation is required. Firstly, we'll have an introduction about why solar energy needs to be conserved. Secondly, we'll study the advantages of solar power generation over other renewable energies. Thirdly, we'll study that what is actually a solar cell and what is the photovoltaic phenomena. Then we'll study the parameters on which solar cell works. Then we'll study that why we need thin film solar cells. Then we'll classify the different types of solar cells and we'll study their advantages and disadvantages. Then we'll study the types of thin film solar cells and their advantages and disadvantages. We'll study the structure and working of thin film solar cells. And in the end, we'll study the merits and demerits of thin film solar cell and the possible applications. So to begin with, let's have an introduction that why do we need to conserve solar energy. While a majority of the world's current electricity supply is generated from fossil fuels such as coal, oil, natural gas, these traditional energy sources face a number of challenges including rising prices, security concerns, over-dependence on imports from a limited number of countries which have significant fossil fuel supplies. And then there are growing environmental concerns over the climate change risk associated with power generation using fossil fuels. As a result, and other challenges facing traditional energy sources, government, businesses and consumers are increasingly supporting the development of alternative energy sources and new technologies for electricity generation. Renewable energy sources such as solar energy, biomass energy, geothermal, hydroelectric and wind power generation. All these energies have emerged as potential alternatives which address some of these concerns. As opposed to fossil fuels, which draw on finite resources that may eventually become too expensive to retrieve, renewable energy resources are generally unlimited in availability. Solar power generation has emerged as one of the most rapidly growing renewable sources of electricity. Solar power generation has several advantages over other forms of electricity generation. The advantages are listed below. First of all, there is reduced dependence on fossil fuels. That is, solar energy production does not require fossil fuels and is therefore less dependent on this limited and expensive natural resource. Although there is variability in the amount and timing of sunlight over the day, season, and year, a properly sized and configured system can be designed to be highly reliable while providing long-term fixed price electricity supply. The next advantage is environmental changes. Solar power production generates electricity with a limited impact on the environment as compared to other forms of electricity production. The third advantage is matching peak time output with peak time demand. Solar energy can effectively supplement electricity supply from an electricity transmission grid, such as when electricity demand peaks in the summer. The next advantage is modularity and scalability. As the size and generating capacity of a solar system are a function of the number of solar modules installed. Applications of solar technology are readily scalable and versatile. Then the next advantage is flexible locations. Solar power production facilities can be installed at the customer site, which reduces required investment in production and transportation infrastructure. Let us study what is a solar cell and what is photovoltaics. Direct conversion of light into electrical energy is called photovoltaics, denoted by the short form PV. Photovoltaic devices which convert solar energy into electricity are called solar cells. Two electronically dissimilar materials with different free electron densities are brought together to form a junction with a barrier, forming a photovoltaic device. Typical examples are, let's have a metal 1, oxide and metal 2. This is form a junction and it will be a photovoltaic cell. Another example is metal semiconductor, Schottky type contact solar cell. Then the next is the most convenient and the most conventional, which is the p-type semiconductor joined with the n-type semiconductor. When the same type of semiconductor is made p-type and n-type, that is the homojunction based solar cell. Then another one is p-type semiconductor 1 and n-type semiconductor 2, which will be a heterojunction based solar cell. Next is n plus and minus n semiconductor. Another one is having a p-type material. In between there is a insulating layer, and then there is a n-type semiconductor layer. Then this junction will again be a solar cell. Then there will be the multi-junction solar cell, in which this pin arrangement, that is p-type, insulator and n-type, will be repeated over the multiple layers. That will be the multi-junction solar cell. The next is a tandem solar cell, which will have the multiple repetitions of multi-junctions. So it will have a junction 1 having multiples of multi-junction, then junction 2 having multiples of multi-junction, and so on. That will be called as a tandem solar cell. Now let us see what is a solar cell and the parameters on which solar cell operates. Solar cell operations depend upon, number 1, absorption of light to create electron hole pair, that is the carriers, in which the carrier is the electron hole pairs. The next criteria on which solar cell operation depends is the diffusion of carriers. Then thirdly, it depends on separation of electrons and holes. Then next, it depends on collection of carriers. A solar cell is a light driven battery with an open current voltage and a short circuit current, maximum power point current and voltage, and a series and a parallel resistance. Solar cell efficiency is given by eta equals to output voltage upon input voltage, या output upon input, which is equals to Im into Vm divided by summation n into h into V, which indirectly equals to ISI or ISC into VIL into Ft divided by summation nh nu, which depends, that means solar cell efficiency depends on quantum efficiency of creation of carriers, effectiveness of separation of carriers before recombination, and collection of the separated carriers. The highest theoretical efficiency of known materials are as, for homojunction, the highest efficiency known is 30%. In case of heterojunctions, it is 42%. And the solar cell based on tandem multi-gap junctions is approximately 76%. Let us see why do we need thin film solar cells. Number 1, small thickness is required due to the high absorption, small diffusion length is required, and high recombination velocity is required for the high performance of a solar cell. And in thin film, we meet all these criteria. Secondly, materials economy, very low weight per unit power is required. which is again fulfilled by the thin film solar cell. Thirdly, various simple and sophisticated deposition techniques which can be easily used for the thin film solar cell. Then next is the variety of structures available: amorphous, polycrystalline, epitaxial, which is includes and creates the flexibility in the solar cells, which can be attained in the thin film solar cell. The last one is the topography, ranging from very tough to atomically smooth. Entire range can be achieved and can be explored using thin film solar cells. Then in thin film solar cell, different type of junctions are possible: homojunction, heterojunction, Schottky type junction, etc. Then tandem and multi-junction cells are also possible using thin film solar cells. Next, in situ cell integration to form modules is possible using thin film solar technology. Then the thin film solar cells are compatible with solar thermal devices. And in the end, there is a ability of tailoring various optico-electrical and optoelectronical properties, for example, energy gap, electron affinity, walk function, graded gap, etc. using thin films. Now let us discuss the various types of solar cells. The first category of solar cells is the monocrystalline silicon solar cells. Solar cells made of monocrystalline silicon, also called single crystalline silicon, are quite easily recognizable by an external even coloring and uniform look, indicating high purity silicon. As you can see, monocrystalline solar cells are made out of silicon ingots which are cylindrical in shape. To optimize performance and lower cost of a single monocrystalline solar cell, 4 sides are cut out of the cylindrical ingot to make silicon wafer, which is what gives monocrystalline solar panels their characteristic look. A good way to separate mono and polycrystalline solar panel is that polycrystalline solar cells look perfectly rectangular with no rounded edges. Let's study the advantages of the monocrystalline solar panels. So the main advantage is the monocrystalline solar panels have the highest efficiency rates since they are made out of the highest grade silicon. The efficiency rate of the monocrystalline solar panels are typically 15 to 20%. SunPower produces the highest efficiency solar panels on the US market today. Their E20 series provide panel conversion efficiencies of up to 20.1% that has been updated in April 2013. SunPower has now released the X series of the solar cells at a record-breaking efficiency of 21.5%. The next, monocrystalline solar panels are space efficient. That is, since these solar panels yield the highest power outputs, they also require the least amount of space compared to any other type of solar cell. Monocrystalline solar panels produce up to 4 times amount of electricity as thin film solar panels. The next, monocrystalline solar panel live the longest, that is the durability. Most solar panel manufacturers put a 25 years warranty on their monocrystalline solar panels. Then, monocrystalline solar panels tend to perform better than similarity rated polycrystalline solar panels at low light conditions. Now let us discuss the disadvantages of single crystalline or monocrystalline silicon solar cells. Monocrystalline solar panels are the most expensive. From a financial standpoint, a solar panel that is made of polycrystalline silicon and in some cases thin film solar cells can be a better choice for some home owners. Secondly, if the solar panel is partially covered with shade, dirt or snow, the entire circuit can break down. Consider getting microinverters based on central string inverters if you think coverage will be a problem. Microinverters will make sure that not the entire solar array is affected by shading issues, with only one of the solar panels. The next disadvantage is the Krosowski process is used to produce monocrystalline silicon. It results in large cylindrical ingots. Four sides are cut out of the ingots to make silicon wafers. So a significant amount of the original silicon ends up as a waste. The next disadvantage is monocrystalline solar panels tend to be more efficient in warm weather. That is, their performance suffers as temperature goes up, but less so than polycrystalline solar panels. For most homeowners, temperature is not a concern. The next category of solar cells is polycrystalline silicon solar cells. The first solar panels based on polycrystalline silicon, which is also known as polysilicon and multicrystalline silicon, were introduced to the market in 1981. Unlike monocrystalline based solar panels, polycrystalline solar panels do not require the Krosowski process. Raw silicon is melted and poured into a square mold, which is cooled and cut into perfectly square wafers. Now let us discuss advantages of polycrystalline silicon solar cells. The process used to make polycrystalline silicon is simpler and it costs less. The amount of waste silicon is less as compared to monocrystalline solar cells. Secondly, polycrystalline solar panels tend to have slightly lower heat tolerance than monocrystalline solar panels. This technically means that they perform slightly worse than monocrystalline solar panels at high temperatures. Heat can affect the performance of solar panels and shorten their lifespans. However, this effect is minor and most homeowners do not need to make it into account. The disadvantages of polycrystalline based solar panels are, first of all, is the efficiency. The efficiency of polycrystalline based solar panels is typically 13 to 16%. Because of low silicon purity, polycrystalline solar panels are not quite as efficient as monocrystalline solar panels. Secondly, low space efficiency. We generally need to cover a larger surface to output the same electrical power as we would get with a solar panel made of monocrystalline silicon. However, this does not mean every monocrystalline solar panel performs better than those based on polycrystalline silicon. Monocrystalline and thin film solar panels tend to be more aesthetically pleasing since they have more uniform look compared to the speckled blue color of polycrystalline silicon. The next type of solar cell is the string ribbon solar cells. String ribbon solar panels are also made out of polycrystalline silicon. String ribbon is the name of a manufacturing technology that produces a form of polycrystalline silicon. Temperature-resistant wires are pulled through molten silicon, which results in very thin silicon ribbons. Solar panels made with this technology looks similar to traditional polycrystalline solar panels. Evergreen Solar was the main manufacturer of solar panels using the string ribbon technology. The company is now bankrupt, rendering the future of string ribbon solar panels unclear. Let us see the advantages of string ribbon solar cells. The only and the main advantage of string ribbon solar cells is the manufacturing of string ribbon solar panels only uses half the amount silicon as monocrystalline manufacturing. So this contributes to lower cost. Let us now discuss the disadvantages of string ribbon solar cells. First of all, the manufacturing of string ribbon solar panels is significantly more energy extensive and more costly. Secondly, efficiency is at best on par with the low-end polycrystalline solar panels at around only 13 to 14%. In research laboratories, researchers have pushed the efficiency of string ribbon solar cells as high as 18.3%. Thirdly, string ribbon solar panels have the lowest space efficiency of any of the main types of crystalline based solar panels. The next category of solar cells is the thin film solar cells, which are also called as TFSC. Thin film solar cells are the new generation solar cells that contain multiple thin film layers of photovoltaic materials. The thin film solar cells are also known as thin film photovoltaic cell. The thicknesses of thin film layers are very less, as few nanometers, compared to traditional PN junction based solar cells. According to the type of photovoltaic material used, the thin film solar cells are classified into four types. The four types of thin film solar cells are: number 1, amorphous silicon and other thin film silicon solar cells; number 2, cadmium telluride based solar cells; number 3, copper indium gallium delecinide or CIS or CIGS solar cells; number 4, dye sensitized solar cell, that is DSSC, and other organic solar cells. Thin film solar cells provide better ways to produce electricity from sunlight than any other method. We can implement these panels in forest areas, solar fields, traffic and street lights, and so on. The cost of this panel is very less as compared to the older silicon wafer cells. Let us now discuss the structure of thin film solar cell. The structure of thin film solar cell is shown below in the given figure. The structure and functioning of thin film solar cells are almost same as that of normal silicon wafer cells. The only difference is in the thin flexible arrangement of the different layers and the basic solar substance used. The thin flexible arrangement of the layers helps to reproduce very thin form of cells which are more efficient than the conventional silicon wafer cells. In the figure given below, you can see that there are two contacts. The top contact is the transparent conducting coating, TCOs, which we studied in our previous module on optical coatings. Then there is anti-reflection coating. Between the anti-reflection coating and the lower bottom contact, which is an ohmic contact, there is a junction formed between two semiconductor materials. That is, first of all, in green color you can see the substrate. Then above the substrate we have the bottom electrode, which is having an ohmic contact with the actual layers, which leads to the photovoltaic phenomena. So over the substrate there is an ohmic contact, which is a bottom electrode. Then there in the between there is a junction formed using the two layers of two different semiconductors. That is, the bottom is a p-type absorber layer formed by the second semiconducting material, and above that there is a top n-type window layer formed by first semiconductor material. Then there is a anti-reflection coating on the above layer, that is on the top n-type window layer, and above that there is a transparent conductive coating. So this is the structure of a thin film solar cell. Let us now discuss the working of a thin film solar cell. The basic substance of a photovoltaic cell is semiconductors. The semiconductors doped with phosphorus develops an excess of free electrons, usually called n-type material, and a semiconductor doped with boron, gallium or indium develop a vacancy, which are called as holes, and these doped materials are known as p-type materials. So these n-type and p-type materials combine or join together to form a photovoltaic cell. During the absence of light, a very small amount of atoms are excited and move across the junction. This causes a small voltage drop across the junction. But in the presence of light, more atoms are excited and flow through the junction and cause a large current at the output. This current can be stored in a rechargeable battery and is used for several applications based on the requirement. So the old solar panel technology used silicon semiconductor for the production of p-type and n-type layers and has several disadvantages. But in the case of thin film layer technology, The silicon semiconductor materials is replaced by either cadmium telluride, that is CdTe, or copper indium gallium diselenide, that is CIGS. You can see in the given figure the basic structure, taking an example of various semiconductor as a thin film solar cell in which there are two electrodes you can see of nickel and aluminium. Then there is zinc oxide layer, CDS layer and CIGS layer, and below there is a substrate. This is a schematic diagram of a CIGS solar cell. Let us study about the various types of thin film solar cell. The first type of the thin film solar cell is the amorphous silicon or ASI solar cell. Because the output of electrical power is low, solar cells based on amorphous silicon have traditionally only been used for small scale applications such as in pocket calculators. However, recent innovations have made them more attractive for some large scale applications too. With a manufacturing technique called stacking, several layers of amorphous silicon solar cells can be combined, which results in higher efficiency rates, typically around 6 to 8%. Only 1% of the silicon used in crystalline silicon solar cell is required in amorphous silicon solar cells. On the other hand, stacking is expensive. The next type of thin film solar cell is the cadmium telluride, that is CdTe solar cells. Cadmium telluride is the only thin film solar panel technology that has surpassed the cost efficiency of crystalline silicon solar panels in a significant proportion of the market, that is multi-kilowatt systems. The efficiency of solar panel based on cadmium telluride usually operates in the range 9 to 11%. First Solar has installed over 5 gigawatts of cadmium telluride thin film solar panels worldwide. The same company holds the world record for cadmium telluride photovoltaic module efficiency of about 14.4%. The third type of solar cell, that is a thin film solar cell, is the copper indium gallium selenide or CIGS solar cell. Compared to the other thin film technologies above, CIGS solar cells have showed the most potential in terms of efficiency. These solar cells contain less amounts of the toxic material, that is the cadmium, which is found in cadmium telluride solar cells. Commercial production of flexible CIGS solar panels was started in Germany in 2011. The efficiency rates of CIGS solar panels typically operate in the range 10 to 12%. Many thin film solar cell types are still early in the research and testing stages. Some of them have enormous potential and we will likely to see more of them in the future. The fourth type or the fourth category of the thin film solar cell is the dye-synthesized solar cells, DSSC. DSSC is a disruptive technology that can be used to produce electricity in a wide range of light conditions, indoors and outdoors, enabling the user to convert both artificial and natural light into energy to power a broad range of electronic devices. Dye-synthesized solar cells were invented in 1991 by Professor Michael Gretzel and Dr. Brian O'Regan at École Polytechnique Fédérale Lausanne, Switzerland, and is often referred to as Gretzel cell, or we call it as G cell. Most of the material used are low cost. However, a handful of more costly materials are necessary, such as ruthenium and platinum. There is a significant practical challenge involved in designing the liquid electrolyte for DSSCs, which must be able to remain in the liquid phase in all kinds of weather conditions. Even though the conversion efficiency of dye-synthesized photovoltaic cell is lower than that of some other thin film cells, their price to performance ratio is sufficient to make them an important player in the solar market, particularly in building integrated photovoltaic applications. Now let us discuss how DSSC work. The dye is the photoactive material of DSSC cell and can produce electricity once it is sensitized by light. The dye catches photons of incoming light and uses their energy to excite electrons, behaving like chlorophyll in photosynthesis. The dye injects this excited electron into the titanium dioxide. The electron is conducted away by nanocrystalline titanium dioxide. A chemical electrolyte in the cell then closes the circuit so that the electrons are returned back to the dye. It is the movement of these electrons that creates energy which can be harvested into a rechargeable battery, supercapacitor, or another electrical device. Let us study the advantages of dye synthesized solar cell. The advantages are, first of all, they are most efficient third generation solar cell technology available, absorbing more sunlight per surface area than standard silicon based solar panels. Secondly, DSSCs are an attractive replacement for current technologies in low density applications such as rooftop solar collectors, where the lightweight and the mechanical robustness of the printable cell is a key benefit. These may not be as attractive for large scale deployments where high efficiency, high cost cells are most suitable. However, even minimal future increases in the conversion efficiency of the DSSC may make it suitable for some of these applications. The next advantage is DSSCs work even in the low light conditions such as non-direct sunlight and cloudy skies. They are more economical, easy to manufacture, and constructed from abundant and stable resource materials. The mechanical robustness of the DSSC leads indirectly to higher efficiencies at a range of temperatures. Normally, DSSCs are built within just a thin conductive plastic top layer, helping heat to be radiated away more easily and hence operate at low internal temperatures. Now, towards the end of this module, let us discuss the advantages and disadvantages of thin film solar cells. The advantages are, thin film solar cells are easy to handle. Secondly, they are more flexible than conventional solar cells. Thirdly, they are available as thin wafer sheets. And fourthly, they are cheaper than traditional panels. The disadvantages of thin film solar cells are, number one, the less efficiency, that is only 20 to 30% of light are converted into electricity. Secondly, the complex structure. Third, they need to be very careful in handling. And lastly, thin film solar cell can't be used in astronomical devices. Now let us see the applications where thin film solar cells can be used. Number one, thin film solar cell can be used in electronic powering circuits. Secondly, they can be used in home light applications. And lastly, they can be used in solar fields. So students, let us now summarize what we have learned in this module. First of all, we saw that why an energy conservation is required in today's world. Secondly, what are the advantages of solar power generation over other renewable energies? Then we studied that what is a solar cell and what is a photovoltaics phenomena and the parameters on which the solar cell works. Next, we studied in detail that why thin film solar cells are better and they are required. Then we studied the various types of solar cells and their advantages and disadvantages. We studied the different types of thin film solar cells and their advantages and disadvantages. Then we studied in detail the structure and working of thin film solar cells. And in the end, we studied the merits, demerits of the thin film solar cells and their possible applications. Thank you.